Chemical reactions involve the formation of a new substance from reactants. These new substances are known as products. Reactants can react to produce products, but in some cases, products can then react to form reactants. These types of reactions are known as reversible reactions. In a reversible reaction, the following symbol is used in order to demonstrate the reaction goes both ways. Let's take, for example, hydrated copper sulfate. If we were to heat this up and provide enough energy to evaporate all of the water from the structure, we would be left with anhydrous copper sulfate with no water. This is an example of a reversible reaction. If we were to remove water, we would go from the hydrated copper sulfate to the anhydrous copper sulfate. If we were to add water, we would go from the anhydrous copper sulfate to the hydrated copper sulfate. You can think about reversible reactions a bit like a scale. The amounts of products and reactants being produced are constantly fluctuating, but in nature things like to be balanced. This balance can only be achieved if the chemical reaction occurs in a closed system, where new reactants cannot enter and products cannot leave. A state known as dynamic equilibrium is achieved when reactants and products are placed in a closed system and the rate of the forwards reaction, going from reactants to products, is equal to the rate of the backwards reaction, going from products to reactants. If we plot a concentration time graph, we can show dynamic equilibrium by looking at the change in concentration of the reactant and product over time. Dynamic equilibrium is shown to have been established when the concentrations of the reactants and the products remain constant. The chemical system likes to remain in dynamic equilibrium, but the system will leave dynamic equilibrium if there is a change in temperature, pressure, or concentration. Let's have a closer look at the well-known reversible reaction, the Haber process. Nitrogen from the air reacts with hydrogen and it produces ammonia. Let's say that the system is in dynamic equilibrium. What would happen if we were to change the concentration of one of the reactants? Let's say we increase the concentration of nitrogen. The system would no longer be in dynamic equilibrium, and in order to correct this change, we would need for the position of equilibrium to shift to the side that would lower the concentration of nitrogen, and that would be the right-hand side. In this way, more ammonia would be produced and dynamic equilibrium would be re-established. Okay, let's have a look at the effect of changing pressure on the position of equilibrium. Pressure is the force exerted by gas particles on a surface when they hit the surface. We can increase pressure by increasing the number of particles, so they'll hit the sides of the container more frequently. Another way to increase pressure would be to reduce volume, and so those gas particles will hit the sides of the container more often. The last way that we can actually increase pressure would be to increase temperature, because the particles will gain kinetic energy and then they will move around more quickly and so hit the sides of the container more often. Let's have a look at the effect of increasing the overall pressure on the position of equilibrium for the Haber process. Remember, the position of equilibrium will shift in the direction that will correct the change in order to re-establish dynamic equilibrium. Okay, so the first thing that we need to do is we need to balance the equation, which is already balanced, so that's perfect. The next thing that we need to do is to look at the number of molecules that we have on either side of the equation. We use the balancing numbers to help us. So on the left-hand side, we've got 1 nitrogen molecule, 3 hydrogens, so that's 4 in total. And on the right-hand side, we have 2 molecules of ammonia. So where will the position of equilibrium shift? The position of equilibrium will not shift to the left because there are 4 molecules, okay, more molecules being produced when more reactants are being produced. And so if the position of equilibrium were to shift here, that wouldn't decrease the overall pressure. So the position of equilibrium shifts to the right, where there are 2 molecules of ammonia being produced from 4 molecules of nitrogen with hydrogen. And so it shifts to the right to correct the change. By having 2 molecules of ammonia instead of 4 molecules being produced, it will lead to the pressure going down and the change being corrected. Let's have a look at the effect of changing temperature on the position of equilibrium. The forward reaction of the Haber process is exothermic, which means that heat energy is released to the surroundings, increasing the overall temperature. The backwards reaction is endothermic, and so this means that heat energy is taken in from the surroundings into the substance, so the overall temperature decreases. In a reversible reaction, if one direction is endothermic, then the other direction will be exothermic. So if we increase the overall temperature, the position of equilibrium will shift in the direction that will correct the change. So it will shift to the endothermic side, so the left-hand side, to the reactant side. And this will happen in order to take in that heat energy and get back into dynamic equilibrium. Really well done for completing this video and doing some chemistry revision. Please like, comment and subscribe and share this video in order to get it to more pupils like yourselves. All the best and see you in my next video.